Hello students, welcome to my channel Concept Tech 2018. I am Sunanda Manke and this is the series on online electronics laboratory, and this is the part where we'll discuss the lab exercises on filters. Filters are basically circuits which are capable of passing signals with certain frequencies and reject the other frequencies, and this property of filters is called its selectivity. And the frequency response of the filter, basically it's a graph between the voltage gain and the frequency, and with the help of this graph we can differentiate between different filters. The filters are used to separate desired signals from undesired signals. They are used to block interfering signals. They are used for enhancing speech and video signals, and they are also used to vary the or to alter the signals in some other ways, like we can alter the phase or we can introduce delay for the given input frequency with the help of filters. The classification of filters, based on the components which are used in the filters, we have active and passive filters, and based on the frequency we have high pass, low pass, band stop and all pass filters. Passive filters use passive component, that is they use resistor, inductor and capacitor, whereas in active filters we use the active component like amplifiers. Operational amplifier is used with passive components, that is R and C. In the filter, the active devices are used for providing voltage gain. Op-amp provides the gain, and the RC circuit, which is the passive circuit, that is used to provide frequency selectivity. The active filters are normally used below 1 MHz and passive filters are used for high frequencies. Active filters are easy to tune compared to passive filters. This gives the ideal response for the four filters. We have low pass filters which passes low frequencies, attenuates high frequencies. High pass filter attenuates low frequencies, passes high frequencies. Band pass filter passes a specific band of frequencies, and band reject filter rejects or blocks a specific band of frequency. So we have pass band and stop band. The frequency in the pass band are passed through the capacitor, and frequency in the stop band are stopped, blocked or attenuated by the given filter. The assignment includes passive filters and active filters. Passive filters, as discussed, have R, L and C components, whereas in active filters we have operational amplifier with R and C components, resistance and capacitance. Coming to active filters, in active filters we have first order low pass high pass filter, second order low pass filter, Butterworth high pass filter and Chebyshev low pass filters. We'll do all these experiments. And here what do we mean by the order of the filter? Basically, order of the filter depends on the number of RC circuits which are connected in the filters, and the filter response improves as the order of the filters increases. That is, if we have one pair of R and C, then it is a first order filter. If we have two resistors and two capacitors, the filter order becomes 2. So as we go on increasing the number of RC circuits in the filter response improves. This is the lab exercise on Butterworth high pass filter. In Butterworth filter, it is also called maximally flat approximation because the pass band attenuation is 0, so pass band is flat. This particular response is for sixth order filter where A max value is 2.5 dB and the cutoff frequency is 1 kHz. Here 1E2 means 1 into 10 to the power 2, 1E3 is 1 kHz, 1E4 is 10 kHz, 1 into 10 to the power 4 Hz. So in Butterworth filter, pass band attenuation is 0 and it decreases gradually to A max value, and the roll off is 20 dB per decade or 6 dB per octave. Here 20 N dB is written, N stands for the order of the filter. The advantage of Butterworth is its flatness in the pass band, but the disadvantage is roll off is slow. So let's do this experiment. This is Butterworth first order high pass filter. We are giving input and observing output on CRO, and the frequency is 8.2 kHz, and you can observe the output. Output is higher than the input, as you can see here. The lower one is the output waveform, the upper one is the input waveform. If I reduce the frequency to 0.8 Hz, output is almost 0. Right? Being high pass filter, it is not going to pass low frequencies. Output is very small. I have set it to millivolts, right? Output is very small. Now if I increase the frequency and there is an increment in the output amplitude. You can observe the output has increased. We are at 2 kilohertz and output is almost equal to the input applied. You increase it further, output is increasing compared to the input. We have gone to 8 kilohertz and now output is higher than the input applied. So this is a high pass filter. You go to high frequency 12 kilohertz, 122 kilohertz, output is little reduced, and this is 49 kilohertz, 50 kilohertz, output is higher than the input. So this is a high pass filter. It is first order filter, so its response is observed here. It's a Butterworth filter. It gives constant amplitude at high frequencies, as you have observed, and at low frequencies the amplitude is almost zero. This is Butterworth filter, the trainer kit. It is having second order filter as well as first order filter. We have seen the response of the first order high pass filter. Now we'll check the second order filter on the oscilloscope. We have given input through function generator and we will observe output on the CRO as before. It is having two capacitors, so the filter is a second order filter. Let's observe the output. It's a high pass filter, that is, for high frequencies output will be obtained. We are not going to observe the amplitudes, numeric values of the amplitude. We'll just observe the behavior of the filter. As we go on increasing the frequency, being high pass filter, it gives output at high frequencies, and as we go to low frequencies the output reduces. This is 122 kilohertz frequency and we are observing the output. Output is greater than input at such a high frequency also, right? If we go still higher, 1.2 megahertz, it doesn't give you output. 600, 500 hertz, it gives you output. This is 1.2 megahertz frequency and a very small output is obtained. But as we go to 600, 100 kilohertz, output is greater than input. You can observe, right? The lower waveform is the output waveform, the upper is the input waveform, and both are set to same amplitude, and you can observe here output is greater than input. See, output is increasing, and for low frequencies you can observe the output is lower for low frequencies. As you increase the frequency, the lower waveform amplitude increases. We have done this experiment on the trainer kit and the response was observed on the kit. We have applied inputs through function generator and output was observed on the CRO. The kit has first order and second order filter. You can see just one RC circuit and two RC circuits. So this becomes a second order filter. And we have observed the Butterworth response for high pass filter. The response of the second order circuit was better than the first order circuit, and this response was observed. As we increased the frequency above 1 kilohertz, there was a sharp rise in the gain. Up to 1 kilohertz, output was almost constant. So the circuit is working as high pass filter. And as the response was flat in the pass band, the amplitude was more or less constant in the pass band after we increased the frequency. So it is a Butterworth response. I hope you have understood how Butterworth high pass filter works. Thank you.